Okay, welcome to the second video for this week's lecture. So what we're going to be doing in this video is looking at the second fundamental theorem of calculus, as well as a few examples to go with it. Okay? Okay, so this theorem follows on from the first theorem that we just spoke about in the previous video. So basically what it says is that if we've got some function, so if g of x is equal to the integral from some value a up to x of f of t dt, all right, then g dash x, and I should say that f of t is continuous and g of x is differentiable, then g dash x is equal to the derivative with respect to x of the integral from a up to x of f of t dt, all right, which is equal to f of x. Okay, so this is what we call the second fundamental theorem of calculus. So basically what it's saying is that differentiation and integration are opposite processes. So if we've got some function which is the integral from a up to any value of x, then the derivative of that function is simply the original function f of x. Okay. Now a couple of things to be aware of here. First of all, this only applies if we are integrating from some constant a up to some value x, and it must just be x by itself. Not x squared or something else, it must just be x. So if you don't have from a constant up to x, you might need to rearrange your function to be able to do that. And we'll look at a couple of examples where that applies. All right. And secondly, if this is not x, then you'll need to use the chain rule when you multiply down here. Okay. So I'll look at a simple example first, and then we'll look at a couple of complicated examples as well to give you a good broad spectrum of this one. Okay. So let's say that we've got something like so let's say we've got f of x, so capital F of x. Now, it could be capital F of x, it could be capital G of x, it doesn't really matter. So capital F of x is equal to the integral from 3 up to x of sine t squared dt. Okay. Now in this case, we can basically go straight through and say, okay, well f dash x is equal to f of t, which is just this function here. Okay, so it's basically just going to be sine of x squared. All right, and it's as simple as that. So all we're doing is substituting the x in for t. Okay. Now this one is a really straightforward example. We've got a constant up to an x term, so the constant has no effect at all. Okay, it doesn't matter what constant we're starting from. The integral function, the derivative function, is still the same. All right, so this is a really straightforward example of how it works. Basically, all we've done is we've substituted the x for the t. All right. Now, if we have a look at one that's a little bit more tricky than that, so let's say we've got the integral. So let's say g of x is equal to the integral from x to 0 of 5 over 3 plus 2e to the t dt. Okay. Now in this case, when we first look at this one, we go, oh, okay, we're not going from 0 to x, okay, and x is on the bottom. So we need to do something about that. So we need to somehow get x to the top line. Now, what we can do is we can use our knowledge of integral properties, and we know that we can swap these bounds around if we multiply by a negative. So this will become negative, the integral from 0 to x of 5 on 3 plus 2e to the t dt. So now we've got it into the form that we want it for the second fundamental theorem. So what we can do now is we can say, therefore, g dashed x is going to be equal, and we can just, again, substitute in the x for the t. So we've got minus 5 over 3 plus 2e to the x. All right? And this is our derivative of our integral function. So the trick that we use there is swapping the bounds around. So we can't apply the fundamental theorem in this case. We need to make the x be at the top. So we can swap them around and multiply by the negative. All right? Now we'll look at one further example where we have something slightly different to this. So now let's say that we've got f of x is equal to the integral from minus 1 to x squared of 1 on 1 plus t squared. Okay. Sorry, I'm just trying to get my screen right over here, my notes. Okay, now in this case, it's slightly different because this is no longer just x. We've now got x squared. So what we need to do is we need to apply the chain rule, all right? So therefore, f dash x will equal, so we still substitute it in, so it'll be 1 over 1 plus x squared, because it's t squared. But then we need to multiply by the derivative of what's up here, so d by dx of x squared. So this will give us 1 on 1 plus x to the 4 times by 2x. Okay? Alright, which obviously we could write as 2x on 1 plus x to the 4. So there's a couple of variations of the second fundamental theorem of calculus. Alright? Now, again, there's a couple of examples in the workshop this week. There's also a couple of examples in the lecture notes. If you want to practice any, you can just Google second fundamental theorem of calculus as well. All right, that's the end of this video. In the third video, we're going to look at some properties of odd and even functions, which can help us do more complex integrals. All right?